Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a real pleasure for me to welcome back to Microsoft Xiamen Chen, who was previously, I guess it was 2 years ago, an intern with us on the Phoenix project. That work turned out to be very successful, and we ended up, you just lost your display there, ended up publishing a paper in ICDE on how to optimize recovery for Phoenix components. Xiamen was a Microsoft, a holder of Microsoft Fellowship as well, and did a cracker job for us then. I've followed Xiamen's work for a while, and I can tell you that he's doing some of the more interesting work in terms of having systems. Should I keep talking? Let me know how long I need to talk.
4.5 minutes.
Oh, so you're back.
Okay.
Okay. He's been working in the area of how to adapt database systems to the problems of the newer architectures where memory delays are very long compared with CPU cycle times. And as most of you know who attended the ICDE conference, even IBM seems to have gotten that message, and that's part of one of the challenges that Pat Selinger indicated for the next decade. So Xiamen's a bit ahead of the curve on this area, and he's going to tell us about his work in this area today. So.
Thank you. I think a lot of people here are actually quite familiar with CPU cache performance. Right? So today I'm going to talk about rethinking database system designs for exploiting modern computer architecture features. So most commercial database systems today were actually implemented in the 1980s. And in the computer system of 1980s, the main memory was quite close to the CPU, while the disk was very far away from the main memory. So the main memory access latency was roughly the time to execute an instruction, while a disk access costs on the order of the 10 to the 5th memory accesses. And moreover, the memory size was small. Therefore, hard data of the database was primarily on disk. And the database systems use main memory as a cache for disk and build buffer pool structures in main memory. Data pages need to be first read from disk to main memory before being processed. And the disk to memory gap is the traditional focus of database studies. Today, this picture changes. Although the disk to memory gap does not change much, the memory access is very costly now. So several decades of the database studies have proposed a lot of I/O optimizations, and these optimizations have been implemented in the database system today. And moreover, the server systems today have large main memories from several gigabytes to even a terabyte. So more and more hard data can now stay in the main memory, and this is going to be more and more true with the capacity of the memory increasing. So database system today can tolerate the disk to memory gap better. On the other hand, several performance studies on commercial database systems pointed out that over 50% of the execution time in memory is often wasted due to cache misses. And the memory to cache gap is becoming the major performance problem. So let's look at the computer architecture trend to understand the significance of this problem. So this figure plots the memory access latency versus instruction execution time over the years. The y-axis is in log scale. So in the year 1980, on a VAX 11780 machine, the memory access latency was less than the time to execute an instruction. However, today, a memory access can easily cost hundreds of processor cycles. And considering the wide issue rate of the modern processors, a memory access can cost over 1,000 instruction execution opportunities today. And this gap between main memory and CPU is widening exponentially. At the first glance, the disk-to-memory gap and the memory-to-cache gap look very similar. So we are using the main memory as a cache for disk, and we're using the hardware CPU cache as a cache for the main memory. However, they're actually very different. They have very different capacities, block sizes, and latencies. For example, disk blocks are 4 to 64 kilobytes large, while cache lines are only 32 to 128 bytes. Main memory buffers are usually fully associative, while there are some limited set associativities for the CPU caches. Main memory buffers are usually managed by software, while CPU caches are managed by hardware, so it is more difficult for program softwares to control the CPU cache. And the bandwidth sharing properties are different. So I/O bandwidth is shared across all the processes and threads in the operating system, no matter the thread is running or blocking. However, the main memory bandwidth is only used by threads actually running on the CPUs. And if the bandwidth is not used, it is simply wasted. Because of these differences, we have to reconsider the solutions for disk-to-memory gap in the new context. And in many cases, we need to come up with new solutions. There are two general approaches to improving the CPU cache performance of a piece of code. Locality optimizations reduce the number of cache misses, and prefetching reduce the exposed miss latency of cache misses. For example, we can improve the CPU cache performance of matrix multiplication by using a locality optimization technique called blocking. The basic idea is to compute the matrix multiplication through blocked matrix multiplication and make sure the block sizes are small so that all the active blocks can be kept in the CPU cache. In this way, we reduce the number of cache misses by improving the data reuse within every block. However, locality optimizations cannot remove all cache misses. Therefore, we use cache prefetching techniques to hide miss latency for all the remaining cache misses. So modern processors support non-blocking caches, and this means multiple cache misses can be serviced simultaneously in the cache hierarchy. And modern processors support prefetch assembly instructions so that we can insert these prefetch instructions in our code to influence the timing of the cache misses. For example, a piece of code here incurs 2 cache misses because of 2 load instructions. If we know the load addresses early enough, we can issue prefetches early and load data into the cache before the actual execution of the instructions. In this way, we overlap cache misses with computation, and we overlap cache misses with other cache misses. So this is because the memory system can service multiple cache misses simultaneously. Cache prefetching has been shown to be effective on scientific and engineering code, but it has not been well studied in database systems before. Therefore, I exploit cache prefetching for database systems. I focus on intriguing, non-contiguous access patterns because sequential accesses to arrays has been well studied before. I focus on important database structures and operations, specifically index structure and join operation. So in the rest of the talk, I will mainly focus on redesigning index structures, and then I will briefly describe my ideas on the join operations. I will describe related work and conclude with future plans. So index structures are used extensively in databases for fast associative lookups. For example, given the phone book sorted by the name, we want to find out the name and address information for a particular phone number. The brute force way is just to scan the whole phone book, checking every phone record. However, a much better way is to use the index. If we have an index on the phone number, we can directly retrieve the phone record by using the phone number. The common index implementation in databases is B+tree structure. So compared to the familiar binary tree structure, the B+tree is just an n-way search tree. And n is much larger than 2, usually. So for example, to minimize the number of disk accesses, the traditional B+3 node size is the disk page, typically 4 to 64 kilobyte large. So B+3 is a balanced tree structure. All the leaf nodes occur at the same level. A leaf contains a sorted key array and their corresponding pointers to the records in database table. And the leaf also contains a sibling pointer, and the sibling pointer connects all the leaf nodes in key order. All the non-leaf parts of the B+3 are built for the indexing purpose only. A non-leaf node contains a key array and a list of pointers to subtrees. For example, all the keys in subtree 0 are less than key 1. All the keys at subtree 1 are greater than or equal to key 1, but less than key 2. So a search in the B+3 starts from the root node. Here, we do a binary search in the key array and to determine the child pointer to follow. We then follow the child pointer to get down one level. We perform binary search and follow child pointers at every level of the tree until we get down to the leaf level. Here, we do another binary search and retrieve the record pointer to the records in the database table. So there are two common access patterns in B+3. The first is the search-like operation, including insertions and deletions. And insertion deletions begin with a search, followed by some data movements for the updates. The other common access pattern is a range scan operation, which is to locate a collection of records within a key range. For example, the phone company can find out all the customers within the local area code by issuing a range scan with the begin range as 412.00.00 and the end range as 412.999.999. To do the range scan, we first search for the begin key, and then we follow the leaf linked list of sibling pointers to retrieve the record pointers until we encounter the end key. We can see that the search is following a pointer from root to leaf node, while a range scan is following the linked list of leaf nodes. So I take two steps for redesigning B+3s. First, I focus on a pure main memory environment and exploit cache prefetching in this environment for B+3. And then I consider the entire memory hierarchy, taking disk I/O performance into the picture. So to minimize the number of data transfers, we can compute that the optimal node width is the natural data transfer size. For disk, this is the disk page size, which is typically 4 to 64 kilobyte large. For cache, this is a cache line size, typically 32 to 128 bytes large. So compared to a B+3 optimized for disk, a B+3 optimized for cache has much narrower nodes and is much higher. Therefore, its performance is more sensitive to the changes in branching factors. So previous work on cache-sensitive B+3s try to increase the fan-out of a tree node by restricting data layout. So the basic idea is to lay out the child node of a single parent, of the same parent contiguously in main memory. In this way, we only need to keep the pointer to the first child in the parent, and the locations of all the other children can be computed from the first pointer. This essentially eliminates all but one child pointer in all the non-leaf nodes. And if the pointer size and the key size are the same, this effectively doubles the branching factor of cache line-sized non-leaf nodes. So in this figure, I show two sets of experiments, a search experiment and range scan experiment. The y-axis reports execution time normalized to B+3s with one cache line-sized node. So each bar is broken down into three categories. The bottom blue part is the busy time. The CPU is busy executing instructions. The top red part is data cache stalls. The processor cannot make forward progress because of a data cache miss. And the middle green parts are all other stores, for example, because of resource constraints. So we can see that most execution time is wasted on data cache stores. This is even true for the cache-sensitive B+tree case. And compared to B+tree, the cache-sensitive B+tree has faster searches. This is mainly due to the reduction in the height of the tree. However, update performance of CSB+tree is actually worse than B+tree because it wants to keep the continuous layout of the children. And it does not improve the range scan performance. So there's still significant room for improvement. So my solution is to exploit cache prefetching to reduce the amount of exposed mislatency. And the key challenge here is the data dependencies caused by chasing pointers. I will show that my solution can achieve significant performance gains for searches, range scans, and even for updates. And I will show that my scheme is complementary to the CSB+tree scheme. So let's look at a search in a B+tree with node size equals to 1 cache line. So if there are 1,000 keys, and the cache line is 64 byte, and we have 4 byte keys and pointers, there will be 4 levels in the B+tree. A search will cause a full cache miss at each level of the tree. If a cache miss is 150 cycles, a search will cost 600 cycles in total. If we increase the node widths from 1 cache line to 2 cache lines, the height of the tree is actually going to be reduced to 3 levels. However, now we incur 2 cache misses at every level of the tree. And this additional cache miss per node dominates the reduction in the number of levels, and we actually get worse performance. However, things will change if we can exploit cache prefetching. If we prefetch all the lines within the node in parallel, then the 2 cache misses of a node will go out in parallel and be serviced simultaneously in the memory system. And the exposed miss latency of the second cache miss will be much smaller than the full cache miss latency. So my solution for prefetching for search is just to make nodes wider than the natural data transfer size and prefetch all cache lines of a node before searching in the node. Search performance is improved because of the larger branching factors and shallower trees. And at the same time, the cost to access every node is only increased slightly. So we can use this formula to compute the optimal node width. So the time to access a node is equal to a full cache miss latency to load the first cache line, and then exposed miss latency to load the rest of the cache lines. And the search time is equal to a time to access a node multiplied by the tree height, where tree height here is a function of the node width. So this whole thing is a function of node width. Therefore, we can choose the node width to minimize the search time to be the optimal node width. So let's switch to see range scan cache behavior on a B+tree with 1 cache line size node. Here, we incur a full cache miss for each leaf node. Yes?
So I guess my first question is, this assumes that there's spare bandwidth for the cached memory.
Yes.
Is that true in most systems?
So yes, that's right. So if the bandwidth is not used, it will be wasted. The main memory bandwidth can only be used by the threads actually running on processors. And we actually can see. So I have done some experiments with my hash join algorithm later on a 10.2 machine. I'll show you that actually there are plenty of bandwidths. So,
I guess I haven't seen, for SQL Server, which is the database I understand, the case where we have excess cache bandwidth. In other words, say it's a 32 proc machine, you have 32 processors that are asking for memory, right?
Mm-hmm.
And one individual one of them may not be using anything at the time, but there's other ones that are. So the net effect is that our performance is dominated by the number of L3 misses, or whatever, misses not, and there's no extra misses to have that we could use up.
So, how can I say this? So basically, here what I'm trying to do is to overlap the cache misses and try to utilize the parallelism of the memory system. And you can think of the memory system as a queue, right? So each cache miss will be serviced, so basically entered into the queue, and be serviced in the first in, first out order, something like that. So by using prefetching, we actively insert the elements into the queue, right? So if you are not using the prefetching, even you are using 32 processors in the system, you are only just inserting into the queue sporadically. So actually, okay, so how can I say this? Sorry. So okay. So and also the first thing, memory bandwidth is very important. Is the scarce resource. However, it's so even in the multiprocessor system, if it's not a shared bus-based multiprocessor system, so the processor may not share the same memory bandwidth. So it is just NUMA-based, basically. So like you have different clusters of machines sharing the same local memory, and then you have links to visit the remote memory. It's possible that only the clusters sharing the local memory, they share the same memory bandwidth, while across you're not sharing the same memory bandwidth. And also, I think so for applying prefetching technique is the second step. The first step is usually you try to reduce the number of cache misses, and then for those cache misses that you can't reduce, you apply cache prefetching. Okay. Yes.
So are you adding to the memory bandwidth requirements? I mean, aren't these fetches that you have to make anyway? I mean,
well, no. I mean, if you get halfway through the array and you find the child that you want, you don't have to have that second page, right? A second cache line. So on average, you're probably adding. So, my conclusion is you are assuming that there is cache memory bandwidth available for this to work.
Yes, that's right.
Okay. And in some cases there may be. So in which case this helps.
Yes. That's right. Okay. Yes.
So do you organize? So within each node, within each internal node of the CSP plus trace, you have multiple cache lines. But do you store the keys contiguously? So you have to wait for all the cache lines to be loaded, then you can perform the binary search, or you do it some kind of reorganize the keys a little bit. So you can perform some search when you load the first cache line. And if you don't have any, if you found any solutions, you can avoid to load the second cache line.
Okay, so I think the second case, because I'm only issuing prefetches, and then I will go into the loop to do the search. So it just depends on the processor. It will wait for the cache miss to finish, but as soon as the first cache miss finishes, it will go ahead to do the search, the key comparisons.
Did you change the internal organization of a node, or did you change its search algorithm at all?
No.
Just
making
sorting layout
issue.
and binary search. That's what you're doing.
Yes, that's right.
so you are using a binary search.
Here, that's right.
So binary search would, of course, actually touch
differently. That's right. So maybe you can. So the order you issue the prefetches can be tuned. Maybe you can issue the prefetch to the middle of the cache line, something like that. Yes. Okay. So yes. So we incur a full cache miss for every leaf node accessed in the range scan. If we apply the prefetching wider nodes idea, here we achieve better performance this is a definite improvement, but can we still do better? So we want to overlap cache misses until all latency is hidden, or we run out of bandwidth to achieve something like this. But how can we achieve this? Basically, if we represent a leaf node with a yellow rectangle, here we want to overlap the cache misses across leaf nodes. The question is how to achieve this? Okay, so for example, we're currently visiting the blue node, and we want to prefetch 3 nodes ahead. We want to prefetch the red node. A naive implementation is to issue a prefetch instruction like this by using the sibling pointers. However, this won't work. This is because the sibling pointer to the next node is stored in the previous node. And the processor must finish reading the previous node in order to get the address to issue the prefetch for the next node. Therefore, this approach will still experience the full latency at every node. But what we want is really to directly prefetch 3 nodes ahead. So my solution here is to put leaf node addresses into an array conceptually. And in this way, we can use this array to prefetch 3 nodes ahead directly. And we call this array a jump point array. And to initiate prefetching, we also need pointers from the leaf nodes back to the location in the jump point array. And then a jump point array prefetching goes on like this. After searching for the begin key, we follow the back pointer to the location in the jump point array. And then we issue 2 more prefetches. From then on, we visit a node and prefetch 3 nodes ahead until we encounter the end key. Note that here, the prefetch actually goes beyond the end range. But if the range size is large, this overshooting cost is minimum. So here, I prefetch 3 nodes ahead, and this is a tunable parameter called prefetching distance. So we want to make the prefetching distance large enough to hide all cache miss latency. Therefore, if the memory latency is larger, the prefetching distance will be larger. And actually, in this conceptual array organization, we can prefetch arbitrarily far ahead. However, the update cost of this conceptual array is huge. We not only pay the cost of data movement within the array if we do an insertion, but also we need to change the back pointers from the leaf node to the array. So the update cost is huge. To improve the conceptual array design, I make 3 improvements. First, I break the array into a chunk linked list and to limit the impact of the insertion to its own chunk. And then I actively interleave empty slots in the chunk. When I build the array and when I split the chunk, so that an insertion will find an empty slot close to reduce the data movement. And third, I change the meaning of the back pointers from a precise pointer to an approximate pointer. So it still points to the correct chunk. However, within the chunk, the location is approximate. In this way, I can avoid updating the back pointers. But it may require local searches within the chunk to initiate prefetching. But in practice, this part of the cost is very small. So actually, looking at the B+tree structure, there are existing structures in B+tree that contain leaf node addresses. These are the parents of the leaf nodes. If we link the parents of leaf nodes together, we can use them as a jump point array. And we call this implementation an internal jump point array. So compared to the previous external jump point array, an internal array is simpler to implement because most of the maintenance work is taken care of by the B+tree code. And it also consumes less space, although the previous external array already has very low space overhead. However, internal jump point array is less flexible because the chunk size here is fixed by the B+tree structure. And when the memory latency is very large, it may not be possible to fully hide the cache miss latency because you cannot issue prefetch arbitrarily far away. But I didn't see this effect in my experiments. So in my experiments, I assume, yes?
If you This had a larger leaf size. The internal node size could be smaller, but with a large leaf size. Then isn't that equivalent to having these things contiguous in memory? Then you don't need any of these jump arrays.
Yes, but you also change the structure of the B tree. So in the common tree implementation, you fix the node size, right?
Right, but you fix it to this page size, right? Which is already maybe 8 kilobytes or more.
So here I'm talking about
memory blocks
in main memory environment. So here the node size is like a few cache lines large.
But ultimately it's going to be on disk, so
I will talk about the disk problem later in the second slide.
Okay.
So I will answer your question later. So I assume, in my experiment, I assume pure main memory environment. And I insert prefetch instructions into C source code by using GCC inline assemblies. So the performance is measured through detailed cycle-accurate simulations. And the machine model is based on a compact alpha server ES40 system, which has an advanced memory hierarchy. So for the search performance, on x-axis, I vary the number of keys in the tree from 10,000 to 10 million. And I perform 100,000 random searches and report the execution time in million cycles on y-axis. So this first line is the B+3 performance. The B+3 is a one cache line size node. This is the CSB+3 with a one cache line size node. This is the prefetching B+3 with the optimal node size 8 cache lines. And you can see that the prefetching B+3 achieves significantly better performance over B+3 and over CSB+3. If we combine the prefetching wider nodes idea and the CSB+3 idea together, we actually achieve even better performance. This means that prefetching wider nodes idea and the CSB+3 idea are actually complementary. So in the cold cache performance, I perform the same set of experiment, but flash CPU caches in the simulator before every search. And you can clearly see the step-like pattern for every curve. And these steps correspond to the changes in the number of levels in the tree. For example, let's focus on the B+3 curve, which is the top curve. You can see that the number of levels are 5, 6, 6, 7, 7, 8, 8. So clearly, the height of the tree dominates the performance. And this effect is blurred in the previous warm cache case. So for range scan performance, on the x-axis, I vary the key range size from 10 keys to a million keys. And on the y-axis, I report execution time in log scale. So this is the B+3s with one cache line size node. And this is prefetching wider nodes idea, external jump point array prefetching, and internal jump point array prefetching. You can see that the two jump point array implementation actually achieve very similar performance. Focusing on the key ranges that have a larger number of keys, for example, 1,000 and more keys, you can see that prefetching wider nodes idea gave us over 3-fold speed up, while jump point array prefetching gave us an additional 2-fold speed up, and achieving a total over 6-fold speed ups over the baseline B+3. And focusing on the smaller range, you can see the overshooting cost is noticeable. That means we should exploit jump point array prefetching only if the range is expected to be large. Or alternatively, we should search for the end leaf node too and use that as a condition to stop the prefetching to avoid overshooting cost. So in my experiment, I actually observed that insertion performance of the prefetching B+3 is better than the baseline B+3 with one cache line size node. And this is because of two reasons. One, the tree is not very full, and insertions can find empty slots in leaf nodes. The insertion time is dominated by search time. Therefore, faster searches lead to faster insertions. However, when trees are very full, almost every insertion leads to a costly node splits. We actually observe that with wider nodes, there are fewer node splits because of this. So returning to the cache performance breakdown, and add the prefetching B+3 bars, you can see that for search, we eliminated about 45% of the original data cache stores. And for range scan, we eliminated about 97% of the original data cache stores. So in summary, I proposed novel prefetching techniques for search and range scan. And the solution results in faster searches, updates, and range scans. And the technique is complementary to CSP+3s. Yes?
So in your experiment, in your simulators, so how many in-flight cache misses can be served at the same time?
32.
32.
Yes. So on the ES40 machine, the memory system can support 24 in-flight cache misses. So memory system can support 24 outstanding cache misses, and the processor can actually support 32 in-flight stores and 32 in-flight loads.
Can only serve up to 4 outstanding caches.
Yes, but it's so I talked to my advisor, Tom Murray. He's an architect. He told me that it's not very difficult to increase the number of outstanding entries. This is just a buffer. So you just increase some little bit hardware resource. Yes?
So I guess my question was going to be related to that, which was how sensitive are your results to the particular hardware that you're on? I mean, and if in fact you were running on a machine which had more limited capabilities than the alpha which your simulator was tracking.
So first of all, I believe that the range scan performance will always be better. But for the search performance, you can always compute the optimal node widths with some memory. You can measure the memory bandwidth and measure the memory latency and compute the optimal node width. Maybe in some architecture, the optimal node size is just one cache line. So you just don't use multiple cache lines. Roger? No. Okay. So in my second step, I consider the whole memory hierarchy, and this includes the disk I/O performance in the picture. Here, the problem is that previous research proposed B+3s for disk performance and B+3s for cache performance. However, because of the large differences in node sizes, these proposals do not work very well in a different context. For example, if a cache-optimized B+3 cannot fit into main memory, then a search potentially fetch a distinct disk page for every node from root to leaf. And because the tree is much higher than disk-optimized B+3, this leads to many more disk accesses. And disk-optimized B+3s have very poor cache performance, mainly because of the binary search in a large node. So you can think of a binary search in a large array. So you first visit the middle of the array and the quarter of the array, so on and so forth. The first several visits of the large array tends to read a single data item out of a whole cache line and throw away the rest of the cache line. So this poor spatial locality incurs excessive number of cache misses. So because the server has today have large main memories, and so it is possible that a whole B+3 may stay in main memory. And also it is also possible that part of the tree are still code and they are still on disk. So therefore, we are really looking for a single index structure that can optimize for both cache and disk performance and achieve good performance in all these situations. So my approach is to embed cache-optimized trees inside disk-optimized trees. So I call this approach fractal prefetching B+3s because the self-similarity tree within the tree nature of this structure. And here the major challenge is the node size mismatch problem. Basically, a disk page size and cache-optimized node size are determined by hardware parameters and key sizes. Therefore, ideally, we want the cache-optimized trees to fit nicely in disk pages. But usually this is not true. So for example, a 2-level tree may overflow a disk page, or a 2-level tree may significantly underflow a disk page, and adding one more level overflows the disk page. So I propose 2 solutions for this problem. In solution 1, I use different sizes for non-leaf and leaf nodes. So basically, if there's an overflow, I shrink the non-leaf size. And if there's an underflow, I increase the non-leaf size. In solution 2, I do not change the node sizes, but instead, I put the overflowing nodes into new disk pages and let them become the roots of new disk page. So conceptually, the first solution build a disk-optimized B+tree first, and then fit cache-optimized trees into disk pages by varying the node sizes. So I call this solution a disk-first solution. And in the second solution, conceptually, we build a cache-optimized tree first, and then we try to intelligently group the cache-optimized nodes into disk pages. So I call this solution a cache-first solution. So our experiments show that both schemes have very good CPU cache performance. However, only the disk-first solution has good disk performance. The cache-first solution may incur some large disk overhead. So in general, we only recommend the disk-first solution. And the cache-first solution can only be used when there are large main memory and the B+tree can stay in main memory. So this is for search performance. For range scan, we actually can employ gem point array prefetching for both CPU cache performance and for I/O performance. Actually, gem point array I/O prefetching has been implemented in the IBM Universal Database. So, for a set of experiments that use range scan to count the number of entries in the table, this scheme achieves over 2.5-fold speedups on DB2. So next, I'm going to talk about my ideas of improving join operations. So joins are frequently used in databases to connect two tables. For example, a student table contains all the student information, and the take course table contains the grades for students taking courses. And then generating transcripts involves a join operation. Here, the join key is the student ID column. Basically, for every student record, we want to find all the take course records having the same student ID. An efficient way to find matches is to use hash table. So first, we can build a hash table on the student table by hashing on the student ID. And then for every record in the take course table, we can probe the hash table to find the matches. And this is called the simple hash join algorithm. And we call the two tables build table and probe table because of their different roles in the hash join algorithm. So the simple hash join algorithm has a problem. Because of the random access patterns inherent in hashing, if the build table and the hash table cannot fit into main memory, it will incur excessive random IOs. To avoid random disk accesses, the hash join algorithm actually uses a technique called IO partitioning. The idea is to first divide the input tables into partitions with a hash function, and then join pairs of partitions separately using the simple hash join algorithm. And as a result, the algorithm has sequential I/O patterns for both the input tables and the intermediate partitions. And I show in a set of experiments that with advanced I/O techniques such as I/O prefetching and with reasonable I/O bandwidths, hash join can be CPU bound. Therefore, I will only focus on the CPU cache performance of hash joins. So I also take two steps for rethinking hash joins. In my first step, I exploit cache prefetching for the two phases separately. And in the second step, I exploit this two-phase structure to generate some actual information from the I/O partitioning phase that can greatly help the phase 2 of the algorithm. So the challenge of exploiting cache prefetching in this context is that it is very difficult to generate address early. It is very, very difficult to predict addresses because of the randomness of hashing. And also, within the processing of a record, there are data dependencies, and this forms pointer chasing problems. So, but the good news is that we are processing a large number of records, and the dependencies are rare across subsequent records because of the randomness of hashing. Therefore, we can take advantage of this inter-record parallelism and prefetch across. What? Jump to conclusion. I should stop. Okay, so yeah, so I prefetch across multiple records. So I propose two schemes, group prefetching and software pipeline prefetching. These two schemes are inspired by compiler scheduling schemes. However, we can handle the read-write configs and other hash drawing complexities correctly. While these complexities hinder the application of the compiler techniques, the compilers cannot safely prove their transformation. So I want to use conceptual pictures to illustrate my solutions. So the processing of a record can be broken down into several stages. I use digits to represent a different code stage and use line segments to represent different cache misses. For example, stage 0 can be computing hash bucket number from the drawing attribute, and stage 1 can be visiting the hash bucket header. And this cache miss is the cache miss to read bucket header. Therefore, the stage 1 cannot start until the cache miss finishes. Similarly, stage 2 cannot start until the second cache miss finishes, so on and so forth. Therefore, the simple hash drawing algorithm has this cache behavior. There's absolutely no overlap across the processing of subsequent records. In group prefetching, I rearrange the processing of multiple records in a group, like this. I first process the code stage 0 for all the records in the group, and then I issue prefetches for the cache misses, for the first cache misses for all the records in the group. And these cache misses will go out into main memory in parallel and service simultaneously. And then I process code stage 1 for all the records in the group and issue prefetches for the second cache misses, so on and so forth. In this way, I can overlap cache misses across the processing of multiple records in the group. Here, interestingly, in group prefetching, I overlap cache misses across the cache misses with the same color, which means the cache misses of the same memory reference. In software pipeline prefetching, we can achieve a cache behavior like this. Here, we overlap cache misses across different memory references. So I did experiments, recently I did experiments on an Itanium 2 machine and showed that my schemes can achieve up to twofold speedups for hash drawings. So I also did some simulation study varying the memory latency from 150 cycles to 1,000 cycles. So comparing the performances under different memory latency conditions, the absolute performances of my solutions are very close. That means my solution will be still effective for memory latency in the near future. And a surprising piece of result in my experiment is that contrary to the compiler optimization community's conventional wisdom, group prefetching is actually better than software pipeline prefetching. This is because group prefetching has a simpler implementation to deal with the hash code complexity, hash drawing code complexities, and this leads to lower overhead. So in the second step, I exploit the two-path structure of the hash drawing algorithm. Basically, we can inspect data almost for free during the I/O partitioning phase. And then we can use this information for optimizing the drawing phase of the algorithm in two ways. First, we can directly accelerate a new cache-friendly drawing phase algorithm called cache stationary drawing. And then, based on the information about the data, we can choose the most suitable algorithm for the drawing phase. For example, we consider the situations where the two input relations are nearly sorted, or there are a lot of duplicate keys in the input relations. So the idea behind the cache stationary drawing phase is that the I/O partitioning phase can, by using a special index, it can approximately find out the approximate matching relationship between the two input tables. And then the cache stationary join phase can reduce the number of cache misses by taking advantage of this information. And the important thing is that it does this without any additional copying. So that's why I call it cache stationary. And the cache stationary join phase combines cache prefetching and locality optimizations to reduce the memory bandwidth requirement. This is important for shared bus multiprocessor systems. And it's also important for the new multi-threaded and multi-core architectures, because there the off-chip memory bandwidth is shared by all the threads and cores on a single die, and it's very valuable resource. So experimental results through simulation show that when there are 8 or more CPUs in a shared multiprocessor system, we can achieve, by using cache stationary join, we can achieve up to 1.4x speedups over cache prefetching algorithm. So in related work, for B+3 cache performance, there are a couple of proposals to increase the fan-out of the one cache line size B+3 node by restricting data layouts in cache-sensitive B+3s and by compressing keys in partial key trees. Also, Joe and Ross proposed techniques for improving the throughput of a large number of searches in B+3s. The basic idea is to create a buffer, create buffers at the tree nodes to group all the searches reaching the same tree nodes in order to reuse the tree nodes for multiple searches to reduce cache misses. And Chai et al. Proposed a cache-sensitive concurrency control scheme based on optimistic concurrency control. I believe that all these techniques are complementary to my scheme, and they can be included in my scheme. So Hankins and Patel studied the optimal node sizes while considering TLB misses and instruction cost in addition to cache misses. And they found that the optimal node size can be as large as 512 bytes, which is multiple cache lines. So these results coincides with our finding about the wider nodes idea. So corroborates our results. And Lomé described a technique called micro-indexing to improve the search cache performance in the disk page for disk-optimized B+3. The basic idea is to keep an array of a few cache lines at the beginning of the page to index the rest of the keys in the page. The search cache performance can be improved by searching this small index first and then go to a narrowed range of keys in the disk page. And Lomé also advocated that the disk page should be broken down into cache-friendly units. And he pointed out that a challenge of doing this is to find an organization that can strike the balance between search performance, insertion performance, storage utilization, and simplicity. So I believe our fractal prefetching B+3 achieved these goals. Graffi and Larson presented a survey on the techniques of improving CPU cache performance for B+3s. They discussed a number of techniques such as key compression, and I think these techniques can be utilized in our system, in our scheme. There is also theoretical work on cache oblivious B+3s, which proposes a structure that can achieve the optimal search performance asymptotically, regardless of the block size. So for cache join cache performance, Shadow et al. Proposed cache partitioning scheme, which is a similar technique to I/O partitioning. The basic idea is to recursively partition the inputs into cache-sized partitions to reduce cache misses. And Banks et al. Further extended this idea to reduce the the TLB thrashing and cache thrashing. But in our experiments, we show that because of this partitioning step, cache partitioning techniques are at least 50% worse than the cache prefetching techniques. And Manigault et al. Proposed techniques to reduce the cost of integer divisions for computing the hash function. They do this by using integer shifts and bit operations. I think their scheme is complementary to our scheme, and we can include their scheme in our solution. So in conclusion, traditional database systems cannot take advantage of the modern computer architecture features. The memory-to-cache gap is becoming the major performance problem of today's database system. So I exploit cache prefetching supported by most processors today. For index structures, I proposed novel prefetching techniques for B+ trees, and I proposed a novel structure to optimize both cache and disk performance. For join operations, I proposed novel prefetching techniques for hash joins, and also exploit the two-path structure of hash joins for better performance. I believe that my techniques will be more and more important with the architecture trends. So for future work, I not only want to work on CPU cache performance and exploit cache prefetching for other algorithms and structures in database systems, I also want to exploit the multi-threaded and multi-core architectures in more and more popular today. Basically, the Intel Pentium 4 machine already supports 2 hardware threads running on a single die. And IBM Power 5 and many other processors support multiple cores on a single die. Actually, this week, Intel has announced their new processor to support 2 cores on a single die. So at first glance, currently a die looks like a minimized multiprocessor system. However, they have different properties than a true multiprocessor system. So data sharing here is across the on-chip cache. Therefore, data sharing across multiple threads, multiple cores on a single die has very low cost. However, off-chip main memory bandwidth is shared by all the threads and all the cores. Therefore, main memory accesses will become more costly. A natural question to ask, a very interesting question to ask, is just how to efficiently use this new architecture for the database system. Thank you. I'm glad to answer more questions. Yes?
So in your simulations, how much were they multi-user simulations or single-user simulations?
Single-user simulation.
Okay. Do you think that in a multi-user simulation, the effect of, I mean, it would very much depend on how homogeneous the workload was, right? But how would the effect of the higher levels of the cache being naturally kept, the higher levels of the tree being naturally in higher levels of cache, affect your results?
Okay. Let's see. Let me see. So actually in this search performance, I perform back-to-back searches. And this already contains the warm-up factor here. So basically some part of so at least the root of the tree will already be in cache for the later searches.
Okay, so these are repeated single-user searches?
Yes.
Okay.
Yes?
Do processors give you any more control over what's in the cache? Can you actually say keep this in the cache or do anything along those lines?
Currently, no.
Is there any talk about that?
Okay, so in the embedded system world, they actually can have a scratch area in the cache and just write to the cache, and that part of the cache can be controlled by the software. And I think, so I talked to my advisor, and the architectural world, in the architectural world, people are very flexible to new cache schemes. They really want to maybe make some little changes in their cache scheme to support a better and faster application, especially database application. So another very profitable area to work in is to just maybe study the changes of some cache schemes in order to support faster database operations.
Okay. So for this work, you were going on the assumption that the only thing you can do is just issue prefetching.
Yes, it's only on the software side, basically, taking advantage of the existing hardware features. Okay.
Thank you very much.
Thank you.